Welcome everybody. Thank you for joining us, online participants and CSIC colleagues in the room. I am delighted to introduce our very own Dr. Farhad Huseynov. For those of you who don't know Farhad as well as some of us, Farhad joined us in the throes of the first lockdown in March 2020. And he joined us from an engineering consultancy role in Ireland, but prior to that, he had been both working for James Brownjohn, who's an academic in Exeter, doing bridge monitoring activities and doing his PhD at University College Dublin with Professor Eugene O'Brien. So he's got lots of experience in this space. He joined us to be part of the Staffordshire Bridges team and pick up what has been a very long-running project. It's been going for about 9 years now, with this sort of quasi-continuous monitoring and more recently actually continuous monitoring of these bridges from their inception to the present day being in use. So Farhad, I leave the floor to you.
Thank you very much, Jennifer, and good afternoon, everyone. As Jennifer introduced, I'm Farhad Huseynov. So today in this presentation, I will talk about the research project that I've been involved for the last 3 years, but the project itself actually started back in 2015. The name of the project is Long-Term Performance Monitoring of Staffordshire Bridges, which is located in Stafford, UK, using digital twins. The main objective of this project is to demonstrate the practical application of real-time structure health monitoring integrated with digital twins in order to quantify the performance of two instrumented railway bridges owned by Network Rail. So I will give this presentation in two parts. In the first part, I prepared some very short presentation where I will talk about the motivation behind this project and give a background information and explain the monitoring system we've instrumented on two railway bridges. And in the second part, which should be a more interesting part, I will give the live demonstration of the digital twin system that we have developed in the scope of this research project. First, let's talk a little bit about motivation. So the motivation behind this research project always comes from the challenges and limitations practitioner engineers face in the practice. So the current bridge maintenance and assessment practice largely depend on visual inspection, and as all of us know, visual inspections, apart from being very expensive and time-consuming, it only provides qualitative results, and it's prone to errors due to human factor. As a result, thousands of bridges in the UK, and it's the same in all over the world, are reported are deemed as structural deficient, and because visual inspections they're very conservative, provide conservative results. So these structure deficient bridges, some of them they're being demolished and replaced, and many of them they put weight restrictions, which has huge impact on the economy and the environment. And it's before discussing about quantitative based bridge assessment or evaluation approaches, it's I think so although in practice lots of bridges are deemed structurally deficient, but in literature actually the studies tell a completely different story. Many bridges which are tested to failure, it was demonstrated in various structures, in various studies, that bridges actually much stronger than we think. For instance, there's a very good study and paper called Bridge Testing is Surprise Every Time. Authors proof tested dozens of bridges in Canada, and all of them could sustain more loading than reflected by the bridge load postings. Another bridge, like in the US, it was tested to failure, and it could sustain 17 times more than the estimated load, the load estimated using conventional conservative approaches. So it's important to understand where the source of additional strengths have come from. They come mainly from uncertainties involved in the guidelines used by practitioner engineers mainly related how the structural behavior is idealized or material properties used. And one of the main sources of uncertainty is actually traffic loading. Traffic loading being highly variable, obviously. And the traffic load models included in the design guidelines or assessment guidelines are very conservative. As an example, the figure in here, it shows the load model 1. So all highway bridges designed and constructed in Europe should be designed to sustain its load actions. It's a very, like, the dimensions of, it has 2 axles and spaced at 1.2 meter apart. It has exactly the same dimensions as probably the smallest car we can see in the transportation network, smart car, but it has gross vehicle weight of 67 tons, and it's almost 50% heavier than the 4-axle truck with maximum global gross vehicle weight of 40 tons. This 4-axle truck typically, generally imposes the most onerous load actions on a standard bridge, like a span of like 20-30 meters. So that kind of shows how conservative the current design guidelines could be. And normally bridges with multiple lanes, they are loaded with multiple load model 1s. And it's actually specified in Eurocodes that the traffic load models in Eurocodes, they do not describe the actual load. Instead, they're derived to produce the most onerous load actions on any bridge spanning between 2 meters to 200 meters. So they kind of cover a wide range of possibilities and wide range of structural configuration. And this sentence is actually taken directly from the Eurocodes. So that's the main motivation in order to develop a more quantitative and accurate bridge assessment guidelines. So this project started several years ago when Network Rail had a project called Staffordshire Area Improvement, which was going back in 2015. And this project aimed to reduce the bottleneck in these 2 locations, Stafford and near Norton Bridge Village. Eventually, Network Rail built flyovers, and as part of the Norton Bridge project, 10 new bridges were constructed, and our research group were given the opportunity of instrumenting 2 new bridges during the construction phase, called Chelsea and Norton Bridge. They're both located, they're very closely located in near Stafford City. Norton Bridge, it's a half-through composite railway bridge spanning 26.8 meters and has 2 main girders, I-shaped main girders, and Chelsea Bridge, it's a precast pre-stressed concrete bridge with shorter bridge span, about 12 meters. So these are the 2 most common bridge types in the transportation network. Both bridges were instrumented with fiber optic sensors during the construction phase. So for the Norton Bridge, the top and bottom flanges of the both main girders and 2 crosspins were instrumented with FPG sensors. So FPG, they basically measures strain and temperature. Then it's fiber optic cables were also embedded into the reinforced concrete deck slab at the mid-span location, plus pre-stressed slippers were also instrumented with FPGs. Overall, we had 291 FPG sensors on the Norton Bridge. Chelsea Bridge, since it's a precast bridge, the main girders were instrumented with the fiber optic cables at the precast facility. So fiber optic cables were routed along the main along the pre-stressed tendons, and at the construction site again here we instrumented the deck slab at the 1/4 and 3/4 span location. Plus we have 3 pre-stressed sleepers instrumented with FPG sensors. Overall, we have 220 FPG sensors on the Chelsea Bridge. So the first 2 phases of Staffordshire bridges were completed by 2017. The main objective of the first 2 phases were mainly to investigate the feasibility of using fiber optic sensors for long-term bridge monitoring applications. Initially, we didn't have any permanent power on site. We acquired data during short site visits, and that involved basically setting up a tent next to the cabinet and using like generator to power up the data acquisition systems. And the early data acquired from these bridges were mainly used to study the time-dependent behaviors such as pre-stress loss, crack and shrinkage. There's a researcher also looked at the load distribution path from the slippers to ballast and to main load main beams. Then in 2020, we received further funding from CDBB, Centre for Digital Britain, to develop a continuous monitoring system for the Staffordshire bridges using digital twin. So digital twin, it's a realistic representation of an asset of a physical asset in the digital world. So the key aspect of the digital twin is basically, it's one of the main challenges of building the digital twin was providing this connection between the physical and virtual twin. Then our digital twin system, it's empowered with using built-in data processing algorithms, which kind of takes raw site monitoring data and extracts information useful for us or asset managers, such as what's the realistic representation occurring on site, like traffic loading or understanding the structural behavior better. Developing a digital twin system first required basically providing that connection, continuous connection between the physical and the virtual twins. That required setting up a continuous monitoring system. As I mentioned, initially we didn't have any permanent power on site. We asked Network Rail to provide the power, and it was installed back in January 2021. And the cabinet on the right-hand side shows the data acquisition system that we've developed. It's replaced the cabinet. This is the old cabinet that only contained the end of the fiber optic cables, and the new cabinet was replaced, which has the data acquisition and transfer system. And it was installed in November 2021, so almost 2 years ago. While Network Rail engineers were working on site and installing permanent power, we used this opportunity to install some additional sensors for several reasons. One of the main reasons, actually, we wanted to set up a train load monitoring system. Since, as I mentioned, traffic loading is one of the main sources of uncertainties. Setting up a train load monitoring system required an additional information. In addition to deformation and monitoring, we also required like accurate positions of the axles, which wasn't possible to obtain using the existing system, or at least on both tracks. So we developed this axle detection system using laser rangefinder sensor. So laser rangefinder, short name LRF. So LRF is a sensor that beams light at a high frequency in order to measure distance. So they were installed at the start and end of the bridge, pointing to the railway tracks, to both tracks. And the idea is when an axle crosses the center location, it cuts the beaming light, and we identify the presence of axles at the entrance and exit of the bridge from the time history signal. In addition to axle detection system, we also instrumented 4 accelerometers placed at 2 supports, quarter and 3/4 stand locations. And the idea of installing the accelerometer, especially at 2 supports, was using accelerometers. We use accelerometers like asynchronometers. So through the rotation through the gravity, we measure rotation and like how much the deck rotates as it deforms. Plus, we also installed some camera and the temperature and humidity sensor. So this system, the diagram shows the summary of the monitoring system. We have multiple sensing systems, accelerometers, cameras, fiber optic sensors, axle detection system, and temperature and humidity sensor. Our data acquisition system acquires time synchronized data from multiple sensing units and transfers it to the database which exists in this building using 4G data connection. Achieving time synchronization was vital for this project, especially for setting up a train load monitoring system, because the algorithm, which I will explain in the following slides, it kind of looks at the relation of the measured deformation, the axle positions, in order to predict the individual axle weights. And yeah, so once the data is in the database, so our digital twin system, which is integrated with data processing algorithms, processes all site monitoring data and extracts the useful information, which I will show in the next, so this next part of my presentation, I will show the live demonstration of the digital twin system that we have developed. So this is the landing page of our digital twin system. So far, we have developed 4 dashboards, and I will go from each dashboard one by one. Sorry. So the first dashboard is developed to access and visualize the site monitoring data. So the bar plots at the top, it shows the daily train crossings. So in average, I mean, up until recently, we were getting like 80, roughly between 60 to 80 daily trains crossings, but then recently, throughout this summer, the daily train crossings increased somewhere between 80 to 100. So far, we have acquired data during the crossing of more than 42,000 trains. And then we have the timetable, we have the calendar and the timetable that allows us to go back in date all the way back to November 2021, pick up and basically select any train crossings, and then we see here a Super Voyager Class 220 or 221 train crossing our bridge site, and we have these temperature and humidity time series. Then we have 4 accelerometers, and then we have FPG and fiber optic, this train data. We have 16 cables. Each cable either has 20 or 7 sensor nodes. And then here we have these time series from the axle detector. So each peak corresponds with the axle entering or leaving the bridge. So these 2 closest space peaks, they correspond to the passage of a bogie. And we have this sensor node, that's the entrance of the bridge, and we have south, which is the exit of the bridge. So we have, knowing the axles entering and leaving, we can basically predict the speed and then identify the position of individual axles at any point in time. So that's the first dashboard, which basically we mainly use for visualizing, accessing data. The second dashboard that we've developed, it's for the real-time train load monitoring system. So we developed this train load monitoring system based on a technology called bridge weighing motion technology. So I've included 2-3 slides to explain what BWIM system is and what it does. So BWIM is a system that it uses the deformation induced by passing vehicle, and it solves an inverse type problem. It back calculates the axle weights using basically the algorithm is based on the influence line, and it predicts the axle weights based on the fact that the deformation response is equal to the sum of the product of the axle weights and influence line. So influence line, it's the response of a bridge to a single moving unit loading. So bridge weighing motion installation typically requires calibration during the installation phase, and influence line is first obtained using the deformations obtained during the passage of a vehicle with known axle weight. So in the expression, basically, deformation is always known because we measure it, and the axle weights of the test track is known, and the only unknown in the expression is the influence line that we obtain during the calibration phase. Then once the influence line is obtained, then during the operation phase, and the only unknown becomes the axle weights, which basically the algorithm predicts. To calibrate the BWIM system, we use the deformation response acquired during the passage of this new measurement train, or the nickname is a yellow banana train because of its color. So it's a train developed by Network Rail to assess the condition of railway tracks. As you can see here, the train crossing our bridge side, and it will basically it has laser scanners. This train instrumented with laser scanners, some gyros, accelerometers, etc. These laser scanners scan the railway tracks by beaming light, as you can see in this video. And axle weight has a fixed weight, which is known to network rail, and the column on the right-hand side is the axle weights that's provided to us by network rail. The figure on the left-hand side, it shows the axle detection output from the laser rangefinders. And the plot on the right-hand side, it shows a typical strain time history signal from a sensor at the mid-span at the top and bottom flanges of one of the main girders. And here the red and blue data markers, it represents the axles entering and leaving the bridge. So for instance, at any point in time, let's say at 16 seconds, so we know that there is 1, 2, 3, 4 bogies have already entered the bridge and 1 bogie has already left the bridge. And since we know the timestamps axles enter and leave the bridge, we can identify the speed, and from the speed we can identify the axle positions at every point in time. Using this information, we calibrated our bridge vane motion system, which means we obtained the influence line at every single sensor location. So here it shows the 20 influence lines. So that at the top of at the top flange of one of the main girders, or top or bottom, I don't remember, to be honest. So at each along the at the top flange, so there's along this FPG cable, there are 20 sensor nodes, and this influence line basically shows the influence line at every sensor location. So for instance, sensor 10 is located at the mid-span, so it kind of shows that if a unit point load will move along the bridge, it will cause this much strain, which is yeah, I think that's 10 to the power of minus 10. Oh, that's, yeah, so that's the bridge vane motion system. Okay. So let's do some train spotting. So for instance, here it shows a Super Voyager train crossed our bridge site about 10-15 minutes ago. Yes, it's class 221, it's British Rail class 221 train, which has 20 axles. It has 5 passenger cars, so it has 20 axles, and it has a gross train weight of 275 tons. So if we look at class 221 train, it comes in 4 and 5 car set formation, and for 5 car set formation, the total gross train weight is 281 tons, and we predicted it at 275. So it's pretty accurate. We did some accuracy study, and for the accuracy of gross train weight accuracy from our train load monitoring system is within the range of, or the error is within the range of ±3%. Can I have a look at maybe I can show you a couple of other trains that crossed our sites. This one in the morning. That's the same type of train. Maybe I'll look in here, it's much easier to. Yeah, that's class 350 train. It's a regional commuter train, which has a gross train weight of 175 tons, and we predicted 182 tons. Next, we developed some unsupervised train classification algorithm based on, we implemented two different unsupervised machine learning algorithms. First, we used an algorithm called T-distributed stochastic neighbor embedding algorithm, which kind of takes our train loading database. It looks like this. So it has, sorry, I can't show it. So basically, it has multiple features, which includes like number of axles, gross train weight, individual axle weights, individual axle spacing, and etc. So this T-distributed stochastic neighbor embedding algorithm, or short name is TESNE. It kind of takes the data, it calculates the pairwise distances of every single data point, and in the original higher dimension space, and it calculates kind of the closest located in data points. It projects it into two-dimensional canvas. So here we can see that we can see clear distinct clusters. Here's one cluster, here's another cluster. So there are small multiple clusters here. So in order to identify the clusters, we use the second algorithm. It's called DB-scan, distribution-based scanning algorithm, and it identified multiple clusters here. So these clusters, it has there are all these clusters, all these here clusters. They are passenger trains, which are almost 95% of the train data. The data set consists of passenger trains. So these 350 trains, they are the regional commuter trains. Then we have Super Voyager trains, which have they're British Rail class 220 and 221. As I mentioned, 221 comes in 4 and 5 car passenger set formation, whereas 220 comes in 4 passenger car set formation. They look exactly the same. The only difference is in class 221, it has tilting axles, so that's why it has slightly increased axle weights. Then another passenger, and then we have this combination of class 220 or 221 trains coupled together, which forms individual clusters. For instance, this cluster here, it's a combination of class 220 with 4 cars and 221 with 5 cars. Here we have 221 cars coupled together. And then the second type of passenger train is this British Rail class 390 trains, or the model name is Pendolino trains. They are, I think, express trains. They are the fastest passenger trains in the UK's railway network, and they either come in 9-car or 11-car set formation. So that's the passenger trains. And then we have here, I think I can zoom here. So, and then we have here freight trains, which have in these 3-4 different clusters, and that cluster is based on the it's either loaded, unloaded, and depending on the length of the freight trains, we have a separate clusters here, which is only the freight locomotives, either come in single, double, or triple combinations. Then we have here the tamping machine trains, which is used for repair purposes, to repair the ballast and etc. And then we have 2 different clusters of tamping machine. Basically, they come either 4, 6, 10, or 8, with 8 axles. And then finally, we have this new measurement train, which I showed in the previous slides, which cross our bridge side approximately every 28 days or every month. That's the new measurement train. And then we have here another small cluster, which is like another old measurement train. And I can show these. I've taken some the timestamps of these trains, which I will show them in 2023 new measurement. I think we have already showed the longest freight train that crossed our bridge side. It was recently crossed on 27th of July at it's with the time difference, it's 22:55. And it's quite long. It has 190 axles. It's so long that we struggle to fit into this plot. It's 784 meters long, almost a kilometer long. Sorry. And then basically the first 6 axles, it shows the crossing of the freight locomotive, which has 2 bogies, and each bogie, most of the freight locomotives has each bogie have like 3 axles, and then the following is the freight wagons. So that's the longest. The heaviest train that we have observed crossing our bridge site, and it was March 15, 12:07. It's this one. So the maximum allowable axle weight on the UK's railway network is on this specific line. There are some lines which has reduced like weight restrictions, but on this line the maximum axle weight is 25 tons and for per axle, and as we can see, this is completely full freight train which has the axle weights are on the limit basically. And it's much shorter, but this is the heaviest in terms of both gross vehicle weight and maximum axle weights. So we can happily say that there's no weight violation happening on our, at least crossing our bridge side. Yeah, there are some other tamping like trains that I can show. It's tamping train, which is, it's again crossed on July. This is the latest interesting trains. Or maybe like it's steam trains are more interesting, I guess. I need to go back in date for 2022 April 27. That's 2018. Yeah, so that it shows a steam locomotive carrying passenger cars and steam locomotive. So basically, and then at the end, it has a normal diesel train locomotive. These first axles, the axle number 4, 5 axles, it corresponds with the steam locomotive, and the following is it's called tender, yeah. And as we can see here, so this is the first bit, and then followed by the tender. Yeah, that's the train load monitoring system that we've developed. The next dashboard, how much time do we have? Maybe 10 more minutes. The next dashboard we have developed is for, it's going to show. It's for the structural health monitoring of the main beams, the main load carrying elements. So this dashboard is basically, it shows the structural utilization of the main beams, and we look at for the ultimate limit state and serviceability limit state. And for the ultimate limit state, but before I mention about this, maybe I will explain what's the utilization. So utilization ratio is the ratio between the structural demand and structural capacity. And the design calculations for this bridge was shared with us by the designer, shared the design calculations, and the governing design criteria for this specific bridge is the flexural bending resistance of the main girders, considering the lateral torsional buckling. So because it's a half-through bridge, which means the cross beams connected with the main girders at the near the bottom flange, which works in tension. So which means the top flange, which works in compression, it's unrestrained in the transverse direction. So that's why the flexural moment resistance considering lateral torsional buckling was the governing design criteria. And this bridge was designed using the design load and then all these conservative design assumptions. It was designed with 87% of the utilization ratio for the ultimate limit state. And for the serviceability limit state, there are basically especially for railway bridges, there's 2 critical SLS serviceability limit state criteria, which is mainly controlling the magnitude of vertical deformations. The 2 main criteria: vertical deformation of the deck, which is basically ensures that there is no unacceptable or excess deformation that will cause excessive rail stresses, and etc. And the second limiting criteria is for the passenger comfort, and that's roughly 37 millimeter. We calculated this using the site monitoring data that we acquired for the flexural bending resistance. We used the strains at the top and bottom flange. So these data points here, it shows this utilization ratio calculated for the east and west main girders during every single train crossing. And as you can see, the maximum utilization ratio, or it's well below 20%. It means that there is 80% strength reserve for this structure. It demonstrates the conservativeness involved in the conventional in the design guidelines. Really, in the plot below, it shows the histogram of utilization ratios, and almost like 99, more than 95% of the train crossings only cause like utilization ratios of less than 7%. So that shows the level of conservativeness in the design guidelines. And again, the same thing can be observed for the vertical deformations. The dashed lines, it shows the limiting criteria for the vertical deformation, including passenger comfort criteria. Here we have, it's an outlier. This is due to sometimes we get this glitch in the FPG sensors. By the way, this displacement is calculated in using the strains at the top and bottom flange of the main girders. So it's calculated curvature, and from curvature we use some polynomial fitting approaches in order to convert them into deformations. Yeah, that's pretty much the digital twin system that we have developed. We also have this final dashboard, which is still incomplete. We've developed this 3D visualization model, where so far we have only included the strain measurements from top and bottom flanges of the main girders. But in the future, we'll have all this useful information that we obtained from this data processing or from other sensors. We plan to project it onto this visualization model for better visualization of the sense, quite smooth. Yeah, this is the end of my live demonstration. And if you have any questions, I will be more than answer them.
Thank you very much, Farhad. We've got questions and